All right, everybody, we have one more T-5 talk for the night. And I'd like to introduce Seth Potter.
I'm going to talk about space resources or solar system properties from the point of view of space resource utilization to enable the exploration and development of space. So a lot of old ideas, but maybe kind of approached in a new way. We need resources for structural materials, propellant, consumables, living space, and I'm going to talk about energy, but mostly from the point of view of the kinetic energy of the planet's motion in its orbit, rather than solar power, as I usually talk about. Now, the reason to do this is the distribution of properties is rather wide and a little bit counterintuitive at times. So I want to rack and stack it in kind of a novel way and see what shakes out of it in terms of dollars. Now, in terms of where the mass is, you can see that for the largest bodies of the solar system, there's such a wide range of masses that the largest bodies are heavier than everything else put together. But the largest body is not necessarily where we want to go to get resources. So let's start with living space. The most usable solid surface area is on the Earth, which is why we're here, and on Mars. And in terms of solid surface, it's a virtual tie, but you can use the asteroids to make your own surface as a million times out of the Earth. Now, Jupiter has most of the solar system's angular momentum, and that everything else includes the sun. So you would think Jupiter is the best place to steal kinetic energy if you want to use it for propulsion, but not always. This is a calculation of slingshot trajectories, with the darker ones, the blue being the grazing angle and the green being 10 planetary radii closest approach. And heavier planets are usually better, but not always. This is in terms of gain factor, in terms of delta V out versus delta V in. And you can see that actually Earth and Venus flyby seem to fare quite well in terms of how much you gain compared to how much you put in. If we're looking at a Mars-based civilization, similar results, but the difference between the various planets in terms of delta V is not as pronounced as it is for the Earth. But looked at in terms of, again, the gain factor, if you're on Mars, it actually pays to go down to the Earth to be flung back out again. That's how much energy you gain from the Earth's motion. And you're actually stealing kinetic energy from the Earth's motion around the sun. So now another figure of merit I looked at is relative moment of inertia, which is a measure of how differentiated the interior is. The more homogeneous it is, the more the stuff you want is near the surface. So, and as far as where that stuff is, for the metals, the asteroids, I like this bottom one, the iron asteroids may actually be stainless steel because they have just the right impurities to make stainless steel, and a mining engineer actually confirmed that with me. For carbon, for organics and synthetics, the atmosphere of Mars and the carbonaceous chondrite asteroids seem to be the best place to get carbon to synthesize all sorts of stuff that you need to live on in space. As helium-3, kind of a speculative idea for fusion power for the Earth, very rare on Earth, parts per million on the outer planets, with Uranus having the lowest escape velocity of the outer planets. That may be the best place to get helium-3, except it's really far. And this is how long it takes to get there on a minimum energy trajectory, or how long to get there and ship the stuff back. And of course, time is equal to money, or more accurately, delta time is equal to loss of money. And this is a plot of net present value loss, or loss of money over time. And you can see this is for different discount rates, and those of you who are into that, you'll see that the loss is highly sensitive to discount rate. Bottom line is faster propulsion is better. So many delta V's, so little time. I didn't have time to do all the synergies, so there's an infinite number. So I just picked one and ran with it, and that was space-based solar power, which for geostationary solar collectors, you probably want to get the resources from the moon, the Earth, and the asteroids. So when you look at the comparative energy or change in velocity it takes to get resources from those places, you'll see that the moon is less than half of what it takes to get stuff from the Earth, and the asteroids potentially even less. So bulk materials from the asteroids, high-value manufactured components from the Earth. In conclusion, I would say that if you're going to get resources from space, you should get them from bodies that are as close as possible but no closer, and as small as possible but no smaller. And this is only the beginning, and I challenge everybody to continue this work and let me know next year what you come up with.